Our next speaker is Vincenzo Savona from EPFL in Lausanne. Welcome, Vincenzo, and we're very much looking forward to your presentation.
Thank you very much. Let me try to share my screen, which is this one. Okay, can you see it?
Yes, we can now.
Okay, and okay, so let me try to go full presentation mode. I should be able to, okay, that's it. So I always show this nice picture of our campus with lake and mountains because I like it very much. Thank you very much. And thank you, David, for organizing this thing. I remember in Melbourne, there was a talk about organizing this online meeting and or perhaps hopefully a physical meeting, and now it must be online for obvious reasons, but it seems to be very successful. So thank you very much for believing in this thing, which is really very interesting. As also the previous speaker, I'm slightly out of topic, perhaps not so much, but I will start talking about quantum, and if ever we want to use the word simulator, that would be more sort of a quantum simulator. What I will show, this is a recent work that we've done in my group. By the way, for those who don't know, I am a theorist in open quantum systems at EPFL in Lausanne in Switzerland. I will talk about purely photonic systems, a model where accounting for the optical nonlinearities, it is possible to reproduce universal properties of interacting spin systems on a lattice, and in particular, the quantum critical behavior of a spin model on a lattice. And this is just using bosons. As we have already heard several times today, it's not a mystery now that photons can simulate many body physics because of optical nonlinearities. In particular, the third order optical nonlinearities. Optical nonlinearity mimics photon-photon interaction, and this is important both at the level of classical physics and most importantly at the level of quantum physics. This happens for polaritons, which are the system that we are interested in most, perhaps during this workshop. This happens for superconducting circuits in a very nice way that can be highly engineered and tuned, and for other kinds of optical resonators. Here's a list of some reviews. I hope you see my pointer. Here's a list of some recent reviews about many body physics with light. Another thing is that optical systems with the classical optical nonlinearities, and this is the topic of this conference, seem to be very well suited for simulating solutions for analog computations of solutions to various optimization problems. As we have already heard this morning in the talk by Natasha, for example, and here I'm giving a widely non-exhaustive bibliography because this is not, strictly speaking, my own field, but there are very recent works, among which a paper by the group of Yoshi Yamamoto that appeared just a couple of months ago on the archive. We will be hearing more about this computation with the classical optics. What I would like to talk about today is this system of quantum optics where a tailored driving field can induce behavior which is exactly that of a quantum spin system. And in particular, after an introduction, I will show two results. The first one is how such a system can display a quantum critical regime. And the second result, which is a bit closer to what we are dealing with today, is that if you assume a frustrated system, so if you assume negative hopping between cavities, which in an equivalent spin system implies frustrated system, then you can mimic, so you can simulate with photons the physics of classical spin liquid. and I will draw some conclusions. All the calculations that you will see are based on the description of a quantum system. So this is a purely quantum model for all what I will show, of a system which is described by an Hamiltonian and coupled to an environment with the Markovian coupling. And this is described by the Lindblad master equation. Okay, and this system, which in the long time limit typically reaches a non-equilibrium steady state, can display dissipative phase transitions. Dissipative phase transitions are similar in their description to quantum phase transitions. In a quantum phase transition, you have a Hamiltonian gap between the ground state and the first excited state that becomes zero for some external parameter. In the case of the dissipative systems, you have the Liouvillean, the super operator corresponding to this expression here that acts on the density matrix. And this object, as a linear operator, has eigenvalues which are complex because the system is dissipative. So this operator is not Hermitian. And there is a zero eigenvalue which corresponds to the steady state, because this is exactly what the eigenvalue that corresponds to no time evolution. And then there is a gap to the next non-zero, to the closest non-zero eigenvalue. And this gap is a measure of the relaxation time of the system, so of the equilibration time of the system, of the time the system takes to reach the steady state, okay? And you can have a dissipative phase transition when this Liouvillean gap by varying some external parameter becomes zero. And so therefore there is a change in the steady state of the system, okay? Now, the particular kind of dissipative system I'm interested in is a resonator with some optical nonlinearities. But what is most important, we assume a two-photon driving and also two-photon loss mechanism. The fact that you have a two-photon loss is just because if you have a physical mechanism for two photons to come into the cavity, then by this channel, you must also assume that there is a loss, two photons at a time. But what is important is this two-photon mechanism. And this two-photon mechanism is very well known because it has been discussed a lot in the context of bosonic codes for quantum computing. So essentially, you can use it to produce what people know as cat states, photonic cat states. I will show the equations later on, but they have been realized experimentally, in particular in the group of Yale, studying superconducting qubits. And essentially, this cat state is a linear combination of two coherent states of light with opposite parity. And it has been shown that these objects can be used as a cat code, as I said, so as a way of encoding a quantum bit in a way that makes it possible to correct for some errors in the quantum computer. And it's also been mentioned as a possible system for modeling spins. Let me explain a bit better how these cat states arise. So we consider a Hamiltonian of a system that is a usual harmonic system plus some kernel linearity, which in the quantum case is modeled as this fourth order term in the Hamiltonian. And then you have, instead of the usual driving term, this Hamiltonian is already written in the rotating wave approximation, you have a term that is quadratic in the creation and destruction operator. So this is a driving term that drives two photons at a time. So presumably you must have a driving field that oscillates at half the frequency and some parametric nonlinear mechanism that it makes it possible to inject photons two at a time, okay? And this Hamiltonian has a very peculiar feature. It is invariant under changing the sign of the field. So it has a Z2 symmetry. It's invariant under a Z2 symmetry. And this system for a single cavity has been discussed at length in the literature. Even the master equation has at least a partially symmetry conserving term, which is the loss term the two photon loss term. However, the single photon loss mechanism, which is present in every cavity, is symmetry breaking, because of course this Z2 symmetry corresponds to the parity. So in terms of number of photons, this corresponds to the parity in the number of photons. And losing one photon, of course, switches the parity from odd to even and from even to odd. In this case, in this system, if you go in the limit of very large driving field, the steady state is approximately a mixed state made by two coherent states, which with opposite phases, so with opposite fields and with equal probability. And this state can be rewritten, so this is a mathematical equality, as a mixture of two ket states, where a ket state now is a coherent superposition of two coherent states with opposite phase. And this is obviously a ket state because it's many photons here, plus many photons there, plus or minus many photons there. So this is the actual ket state. The important thing is that the two ket states are truly orthogonal, whereas the two coherent states are not. And these two ket states can be used as the two states of a quantum bit, or as the two eigenstates of a spin operator. Now, the question is, what happens if we play this physics in a system of coupled resonators? Can it be that by coupling resonators to each other, this system behaves like a quantum spin model in this limit? And in particular, what we would expect, for example, for the quantum transverse Ising model, which, as I will suggest later, it's the model onto which the present bosonic photonic system maps onto. The transverse Ising model has a quantum critical point, so as a quantum phase transition at 0 temperature. From magnetic long-range order at low temperature to, at high temperature, a quantum paramagnet, so paramagnetic system. Okay. Now it turns out that in addition to the quantum phase transition at 0 temperature, there is a regime at low temperatures which is called the quantum critical regime. What are the features of this regime? Well, first of all, I should say that this regime occurs where the thermal energy is smaller, much smaller than the energy associated to the hopping. In this case, what happens is that thermal fluctuations are there, but they don't induce transitions between, so to say, uncorrelated states. They induce a transition, so the thermal fluctuations occur among strongly correlated collective states of the system. And it turns out, and this has been described in several works, and here I cite a couple of references, in particular one where the only experimental observation to my knowledge of this regime, and it has been described at length by Sudhir Sachdev. In this regime, you can have equally universal behavior and universal properties as exactly at the quantum critical point, even though you are at finite temperature. And this is the importance of the quantum critical regime. It's a regime at finite temperature that shows universal properties, universal behavior. Okay, let's try to simulate this. So once again, I will be simulating bosons. So nowhere I will be introducing spins in my system, okay? And what I want to consider is a system which you are all familiar with. So it's a system of interacting bosons with local kernel linearities and hopping. And the only thing is that now the driving field is quadratic, so it's not linear, okay? I will be focusing on an object which is called the parity, the photon number parity. It is this operator here, and it measures exactly the parity in the photon number, so whether the parity is even or odd. And this Hamiltonian conserves this operator. So this operator is conserved by this Hamiltonian. Okay, losses, as I have already said, one photon loss is symmetry breaking, and two photon loss is parity conserving. It conserves the parity, of course. And I will be solving for the steady state of this master equation. And an important thing is that I will be solving this without computing the dynamics, because we have techniques, numerical techniques, to solve directly the algebraic equation with this equality here. This was done first a few years ago by myself in a very simple approximation, which is the mean field limit, in which you essentially apply this approximation, so it becomes a single side problem, which is self-consistently accounts for the field of the other sides. And without going into detail, what happens is that you have a very nice phase diagram with a phase transition as a function of the driving field and of the hopping. This is a phase transition between phase where there is no order parameter, the order parameter here being the expectation value of the field, to a phase where the symmetry is broken, and essentially you get one of these two fields, alpha or minus alpha, with an amplitude larger than 0. Okay, and this is a typical mean field phase transition with the critical exponents which are typical of the mean field phase transition. Okay, so here it's just, there is just this idea that in the in the zero driving field limit, you have essentially the positive ket state, because the positive ket state is the one with an even number of photons, and you have to, by a continuity argument, if you don't drive, you go to ground state, and the ground state has an even number of photons. So by continuity, close to the ground state, you can have only the C+ state, because it's the one with the even number of photons, which dominates the steady state. In the opposite limit, you will have a broken symmetry, and you will have a spontaneous selection of one of these two states. Okay. 2 words about the solution. This was done using this method developed in the group of Cristiano Ciuti in Paris, which is known as the corner space renormalization method, which I won't describe here, but it's essentially a real space renormalization approach to the steady state without integrating the dynamics of the system. And this is quite interesting because you can compute up to an 8×8 array of bosons without approximations, with only, so to say, the approximation, which is, so without physical approximations, with the only approximations being the convergence of the method. And the method can converge well up to arrays of this size. Okay. Okay, so as I said, I want to measure the parity. So what I will do is that I will plot the expectation value of the parity on the steady state for given parameters. And please notice that the nonlinearity here is very, very strong. By strong here, I mean that it is much stronger than the energy scale associated to the single photon loss. This is typically what in a photonic system is described as a single photon nonlinearity, okay? And this is also very hard to obtain, for example, in a polaritonic system, but it can be done in superconducting circuits, for example, okay? However, it is in this regime that we will, that the physics will become, in a sense, more intuitive. We should notice that the physics that I'm describing here is induced by symmetry, so by this Z2 invariance. And the Z2 invariance is present independently of the value of U. So we have to expect that even for weaker nonlinearities, the same physics will occur, or similar physics will occur, but the physics I'm interested in here happens, I mean, I'm assuming very strong nonlinearities, okay? So the parity, well, of course, for a small driving field, as I said, we go to the vacuum, and the vacuum is even, so the parity goes to 1. And as I increase the driving field, the parity decays to 0. Why? Because in the limit of strong driving field, we have seen that the steady state is 50-50 admixture of even and odd ket states. And therefore, the parity is supposed to go to 0. The question is how it goes to 0. And here you see that there are different curves for different system sizes. let's do the following exercise. Let's renormalize the vertical axis here with some scaling function. And then we see that here in the inset, all the curves now meet in one point, which then holds promise to be the critical point of the system, a critical point for the system. And then let's, now that we have found this critical value of the driving field, let's do another exercise, which consists in rescaling also with some scaling function, also the horizontal axis. And we see that all the curves collapse onto the same curve. And this is a very nice evidence of universality for this system. By the way, these results have been published last year in this work that is cited here below. Okay, what are these? What is the scaling function, and what are these exponents? Well, these exponents were not fit. They were just taken from Wikipedia and used. They are the critical exponents of the two-dimensional quantum transverse Ising model. Remember, two-dimensional quantum is equivalent to three-dimensional classical because of the quantum classical correspondence in particular for spin systems. Okay, but the fact that the critical exponents are those of a two-dimensional quantum Ising model, and the fact that we are simulating a two-dimensional system, so we are in two-dimensional geometry, are a very, very strong evidence that here we are observing universal quantum criticality in this system. Okay, and this shows that the quantum criticality is here. Now, we have studied also another feature, which is the von Neumann entropy of the system, which tells us is a way of guessing how much the system is admixed. So how far it is from a pure state. Okay, and what we can see here that the entropy goes to 0, of course. In the limit of low driving, we have one state, and one state means 0 entropy. And in the limit of long driving, of a high driving field, the limit of this value is log 2. And this is also, I mean, this is obvious, but it's quite remarkable because it means that in this limit, the quantum system is stabilizing into a 50-50 admixture of the two cat states, as I have anticipated. But this is now for a huge lattice. So a huge lattice selects just two states, and the steady state is a 50-50 admixture of these two states in the very strong driving field limit. In the middle, you have the appearance of a maximum, okay, for large lattices, and this maximum moves and increases. And although we couldn't go farther away than 8 by 8. We expect that this maximum will become a very sharp singularity at the critical value of the driving field. And if we measure the height of this maximum, we see that it grows with the power law of the system size, so of the number of sites. And this power law is sublinear. And the sublinearity shows that, first of all, there are classical fluctuations in here. Otherwise, the system wouldn't be entropic in a sense. But the sublinear growth shows that at criticality, so at the critical, close to the critical value of G, the system becomes more admixed, but still preserves quantum correlations, because otherwise the entropy would grow as linearly, so it would grow as the number of sites. Okay, so this shows that this is another evidence that the system is behaving in a strongly quantum mechanical way. So these three features essentially are strong evidence that we have a quantum critical regime. And now I would like to draw an analogy between the temperature that plays a role in a thermal system, and in this strongly non-equilibrium system, what plays the role of the temperature is the one photon loss rate, because the single photon loss rate is what induces quantum fluctuations in this limit where only two states are relevant. Okay, and this so we conjecture a phase diagram which has exactly the same shape as the one that you have seen before, but where the role of the temperature qualitatively, I insist on this, not quantitatively. We are not expecting the same quantitative behavior, but qualitatively the role of temperature, namely the source of classical fluctuations, is played by the one photon loss rate, because it flips the spins exactly like the temperature would do in a thermal equilibrium system, okay? And by the way, where does the quantum critical regime occur? Well, it occurs where gamma over j is smaller than 1. So essentially where the structure, where the coarse graining of the system can be traced out. So where the correlation length of the length of the range of the correlations is so large that it doesn't see the lattice. That's the idea. By the way, we recently published a work, and this is the archived version, but it's published by now, where we analyze systems with the lower nonlinearities with a method which is approximate. And although the results are not completely conclusive, we still see very nicely a critical behavior. And the question whether it's of the kind of 2D quantumizing or not is still unclear. And now I would like to finish by telling you what we did more recently. The idea is what happens now if these cavities have a hopping that has the opposite sign, so it's negative. Well, in this case, suppose that the first cavity has alpha as a field in the limit where the symmetry has been broken. Then the other cavity must take minus alpha because now the interaction is negative, and so the hopping is negative. And then we are frustrated because the third cavity in the triangular geometry, we don't know what sign it will take. And this is exactly what we simulated. By the way, J is smaller than 0. Natalia this morning was discussing about hopping. For me, quantum mechanically, the hopping must be real, because if it is complex, the Hamiltonian is no longer Hermitian. I'm sure that classically you can have complex coupling, but this must be mapped to a quantum model where you have some reservoir, engineered reservoir of some kind. This would be an interesting topic for a coffee break if we had coffee break, but unfortunately we don't. Anyway, so once again, we simulated this system purely quantum mechanically, and for some reasons here we need to go to a very large number, very large Hilbert space, which means that we only simulated 3 cavities. So only 3 cavities. This is the maximum we could do. Okay, what do we see? First of all, the first order correlation among sides. This, for the case of 2 cavities, is at -1. Obviously, if you have only 2 cavities, they want to be in opposite signs. But if you have 3 cavities, the frustration gives you, in the limit of large pump, of large driving field, gives you a -1/3, which is exactly what you have if you have all the frustrated states that occur simultaneously in the density matrix. The entropy, so the entropy in the case of 2 cavities goes to log 2 for the same reason that we have seen before. But in the case of 3 cavities, it goes to log 6, because now we have 6 frustrated states that will all exist in a statistical mixture in the limit of large driving field. So the difference between the frustrated and non-frustrated system is striking, because in the limit of very large number of cavities, the entropy of the non-frustrated systems will stay log 2. And the entropy of the frustrated system will be log of the number of frustrated configurations in the system. So it will grow. And finally, by including an external single photon driving, we can test the susceptibility of this system. And this is another interesting test, because in the case of 2 cavities, you get a threshold where you magnetize your system. In the case of 3 cavities, you have a double threshold behavior, which is typical of frustrated antiferromagnets, because essentially you first induce one of the frustrated configuration, and this is the first plateau. And then at even stronger external fields, you break the frustration and you align all the spins. So this is the susceptibility, which has been computed from the bosonic system once again. So we never used spins in here. Okay, so this tells us that systems of coupled cavities with the two photon driving and kernel linearity can simulate some kind of antiferromagnets, of spin antiferromagnets. Which kind? Well, this is interesting because we computed the negativity, so a witness of entanglement for this system, okay? And what we see and what was to be expected is that in the limit of very large driving field, this quantity goes to zero. And if this quantity goes to zero, this means that the system is classical, it's not behaving quantum mechanically. There are no quantum correlations. So essentially what we are simulating with this object, although we had to sweat a lot to solve it in a purely quantum mechanical way. This three-cavity system is simulating the three-site version of a classical spin liquid, which is still the topic of this conference, to solve classical spin models with an analog simulator. Okay, very important. The previous calculations, they were in the strongly quantum correlated regime, which emerges when you make your system bigger and bigger. Here, it's not expected to be the case, but still it's very interesting because it's simulating a classical spin liquid and it's a purely bosonic system. And with this, I come to my conclusions. So two-photon driving in photonic systems can generate a new class of simulators of interacting quantum spin system. And this is essentially my message. The rest is exactly a repetition of what you have seen. An important remark is that two-photon driving is experimentally feasible. Well, it's been demonstrated in superconducting circuits because they are trying to do bosonic codes, but it can be done also for polaritons. We have David Snoke, who was one of those who have succeeded in doing so, and there is another result by Bramati, if I'm not mistaken. And it would be interesting to generalize this to other quantum spin models of interest. And with this, I thank my co-workers, Riccardo Rota, and then collaborators, Cristiano Ciuti in Paris and Fabrizio Minganti, who's now in Japan, in Riken in Japan. Thank you very much.
So thank you very much, Vincenzo. Very interesting talk. We have a question from Vincent Liu.
Yes, perhaps I will unshare my screen to see.
Okay, so before I ask a physics question, I enjoyed the talking about the coffee break, and I want to join Andrew Daney and Dave Sloak from Pittsburgh to welcome you and everybody in the future when we have a physical meeting to have a real coffee break. Anyway, so in Pittsburgh, of course, Dave is the one who did all the organization. Now, physics question. Talk about the two-photon driven system, I mean the resonant system to simulate spin physics. I think it's really fascinating. I wonder actually, was it possible to have a longer range interaction, even like an infinite range interaction?
Well,
by taking advantage of photons, right? For the,
yes.
So it's like go beyond like a typical Heisenberg model.
Yes, I think so. In the case of superconducting circuits, I'm not an expert, but I think this is possible in a one-dimensional geometry, though, because you can engineer almost everything. So you can imagine to build a waveguide which is coupled to cavities, which in turn are coupled to spin qubits, so that the resulting model is that of resonators that are interacting with everybody else through the waveguide. And this has been proposed by several colleagues. In particular, I think that there is a very early proposal by Michel Lukin to do this. It is possible. It is possible, of course. We never tried to simulate, to deal with this hypothesis in our calculations, but it should be possible, of course. In optics, I see it a bit harder, but I mean, perhaps the experimentalists can be more specific on this. I don't know.
For the optical lattice, typically in the cold atoms, the interaction is like a local, I mean, short range, right? Talk about the dipoles. Now I'm really thinking they are fascinating models. I think in the morning, people talking about the SYQ model as models, right? If you have a longer range, like infinite range, you are in the completely different regime, right? So
of course. No, that would be fascinating to have. I mean, to have a quantum or analog simulator or classical analog simulator with long-range interaction. That would be really fantastic, of course. Yes. Okay.
Okay, so I don't at the moment see any more questions for Vincenzo just at the moment. So in the interest of time, I think we'll move on to the next speaker.
Yes.
Vincenzo,
yes,
thank you very much again for the nice presentation.